Hi there, and welcome to this lesson. In this lesson, we'll be learning properties of circles, okay? And then we'll be learning about chords and segments, okay? So the last time we learned about arcs and sectors. This time we're learning about chords and segments. Now, as the lesson progresses, anything you don't understand, be sure to get across to your tutor, who would be more than happy to help. And yes, let's jump right into the lesson. So properties of circles, chords, and segments. Now, last time we talked about chords, okay? We mentioned that a chord is a line that divides a circle into two unequal parts. Okay, it just cuts across a circle. It's like a diameter. It cuts from one point on the circumference to another point on the circumference, but it doesn't cut uh, it doesn't divide the circle into two equal parts the way the diameter does. It just divides the circle pretty much into pretty much anything, basically. And now we're going to be talking about how to find the length of a chord. So if you have a chord cut into a circle in this manner, and you're looking to find the length of this chord, how would you go about finding the length of the chord? If you're given the radius of the circle and the very important property that this chord actually subtends an angle at the center. So we have this chord, and basically we can actually from the two ends of the chord, we can draw two radii down to the center of the circle. Okay, so from the two ends of the chord, and basically based based on the length of the chord, we can actually have an angle here at the center of the circle. So the bigger this angle, obviously the bigger the length of this chord. And up until the point where this angle becomes 180 degrees. And when this angle becomes 180 degrees, this chord becomes a diameter, obviously. But then if we have the angle at the center and we have the chord and we're looking to find the length of the chord, there really isn't a direct formula for doing so. We can generate one, but I'm going to show you a process for finding the length of the chord. Okay, there isn't a direct formula. We would end up with a formula, but I prefer that when you're solving for the length of the chord, use the process. Okay, now when you're looking to find the length of the chord, the first thing I need to do is divide the chord. Okay, so draw a line from the center of the circle that would split that chord into two equal parts. Okay, and basically this would also split the angle theta into two equal parts. And this line obviously would be perpendicular to the chord, and basically we would have 90 degrees there. And now if you look closely, we actually just look right what we have there at the top. Just look at R. Okay, look at where R is. R is the hypotenuse of a right angled triangle, okay, where the opposite of that right angled triangle is C divided by 2, i.e. the length of the chord divided by 2, okay, and the angle in that right angled triangle is theta over 2. Okay, so now you have the radius of the circle as a hypotenuse. You have the angle in the radius of the circle as a hypotenuse. The angle in the triangle is half the angle at the center, and basically you have the opposite as half the length of the chord. So if you're looking to find the length of the chord, you just find that opposite and multiply your answer by 2. And basically to do that, you basically go r sine theta over 2. It gives you the opposite, and then you multiply that by 2. So the length of a chord is always 2r sine theta over 2. Okay, you really don't need to memorize this formula. This is the formula from what we just did. So the length of a chord is always 2r sine theta over 2. But I just explained the process to you. Alright, so if you have a chord, you draw the radius, the ends of the chord down to the center. The angle at the center you divide by 2. It forms a right angle triangle, where the radius becomes the hypotenuse of this right angle triangle. The theta divided by 2 is your angle in the right angle triangle, and then the opposite of this right angle triangle is half the length of the chord. So you find the opposite of that right angle triangle using SOHCAHTOA. Opposite of a hypotenuse equals sine of the angle. So you have that the opposite becomes r sine theta over 2, and then you multiply that by 2 to give you the length of the chord. And that's it. Very simple, very straightforward. Now, another one we're going to talk about is the area of a triangle. Okay, area of the triangle. Basically, let's say you have a triangle in a circle. The triangle that's formed by the radii of the circle, And then basically you an angle at the center. To find the area of this triangle, you just need to apply area of the triangle equals half AB sine theta, where A and B are the sides, are two sides of the triangle, and theta is the angle between those two sides. And basically, if you apply that understanding to what we have here, we actually have two sides of the triangle, R and R, okay? And the angle between the two R's is theta. So basically, if you're looking to find the area of this triangle, you just have half AB sine theta, half RR sine theta, or half R squared sine theta. Finally, area of a segment. So we talked about segments and sectors in the last lesson, okay? We talked about sectors mainly, but then we said a segment is an area like this. Basically, it's an area that's bounded by the circumference and the chord, okay? So the segment is this area here. It's not a sector, it's usually formed right from the center, bound by two radii. But a segment is just basically you cut the circle into two unequal parts, and each of those two parts is a segment of the circle. So you could form any possible way, basically just like the same way you form chords. And then the area bounded by the chord and the circumference around that chord is your segment. Okay, so we have this segment in this case, okay, and we're going to find the area of this segment. Now, to do so, the first thing we will need to find is the area of the sector. Because if you look at this segment and you actually draw from the two ends, you actually form basically, you just look at everything as a whole, right from the center up onto the circumference. That is a sector. And if you look closely, the area of that segment would be the area of the sector minus the area of the triangle. So you have, but it obviously has an angle as well. And basically you actually have an area of a sector here, and you have an area of a triangle. So if to find the area of that segment, you have area of segments denoted with a small s equals area of sector denoted with a big S minus the area of the triangle. And basically what you have is you have area of segment equals, for area of sector you have theta over 360 times pi r squared. And then for area of the triangle you have 1 over 2 r squared sine theta. And basically you find each of them and you just subtract the triangle from the sector. And that is how you find the area of a segment. Very simple, very straightforward. Now let's go ahead and do some examples. We have example 1, and we've been asked to find the length of a chord if it subtends a 72-degree angle at the center of a circle of radius 80 centimeters. Okay, so we have a chord, okay, and it's 70 degrees. The angle at the center is 70 degrees, and we have a circle of radius that, and we have length of chord as 2r sine theta over 2, and we have our r in this case as 80 centimeters, our theta is 72 degrees. So we just go ahead and say the length of the chord would be 2r sine theta over 2. Theta over 2 would be 36. 2 times 80 times sine 36, and you have your length of chord as 10.48. No, that's wrong. Basically, you have your length of chord as that, basically. But yeah, let's do another example. Example 2. Example 2, we have find the angle subtended by a chord 10 centimeters long in a circle of radius 6 centimeters. Okay, so we have our chord and we have our radius, and we're looking to find the angle. We make use of the same formula, and then when we work, we change the subject to formula. We end up with theta equals 2 sine inverse of the length of the chord divided by 2r. And we just go, we say r equals 6, L or length of the chord is 10 centimeters. And we just go ahead and put all of that into the formula. And we should end up with the sine inverse of 0.833. And basically we multiply that by 2, we end up with 102.88 degrees. Final example, and we have find the area of the segment of a circle. So we're looking for segment, and we find sector. we subtract the area of the triangle. We have area of sector as theta over 360 times pi r squared. We have area of the triangle as 1 over 2 r squared sine theta. And we're just going to go ahead and put our information in there. So we have our area of sector as 38.5 centimeters squared. We have our area of triangle as 22.5 centimeters squared. And to find the area of our segment, we just subtract triangle from sector, and we should end up with 16 centimeters squared. So, a circle of radius 7 centimeters with an angle of 90 degrees at the center, you'd form a segment that has an area with an area of 16 centimeters squared. And that would bring us to the end of this very interesting lesson. You can go ahead now and attempt questions in the worksheet. Bye for now.